In SUDOCO, our focus is to address the floating wind sector, and this includes two main responsibilities. The first one is to apply control strategies from bottom-fixed wind turbines or wind farms to floating wind farms, and this is Maarten's expertise, so he will answer you a few questions later. And the second one is to develop a high-resolution monitoring solution specifically for floating wind. So in context of the control room of the future, we address the monitoring of floating wind farms, as this is the foundation to operate a floating wind farm. And then we address the control strategies specifically for floating wind farms.
So, as Niclas explained, floating wind turbines are subject to a whole range of different dynamics due to the interaction of wind and waves. And these interactions play a major role in the performance of the wind farm as a whole, as well as the turbine on its own. Control strategies that may work very well for a bottom-fixed wind farm might not work as effectively for a floating wind farm. So, for example, wake steering, a strategy that works on bottom-fixed wind turbines to deflect the wakes and reduce interaction between wind turbines, does not work as well on floating wind turbines due to the degrees of freedom in the floating platform.
So, as the name suggests, the key difference between bottom-fixed turbines and floating turbines is that the turbines are based on a floating foundation, which is moving around, and therefore it's held in place by mooring lines. And those mooring lines are crucial, but also challenging. They are expensive in procurement and also in installation and maintenance, because you need special vessels to handle them. And another aspect is that they can and do fail, mostly because of fatigue. And therefore it's essential for the wind farm's safety that mooring failures are detected. But ideally, we want to also predict mooring failures before they even happen. However, the most intuitive approach would be to directly measure mooring tensions subsea, but the problem is that those subsea sensors are quite expensive and unreliable in those harsh conditions, especially over the long lifetime of these turbines. And instead, we need a reliable and cost-effective and scalable solution for floating wind farms, and that is not yet available on the market.
We're planning to address these specific challenges for a floating wind farm control by using the sowento expertise on the control of floating wind turbines, where we have extensive experience in developing control strategies and mitigating the issues related to floating wind turbine control, and use this expertise to identify the key performance indicators required to assess wind farm control and run numerical simulations of floating wind farms to evaluate what the key issues are in transitioning from fixed bottom wind farm control to floating wind farm control.
We are focusing on physics-based models instead of AI or machine-based models. And with our sowento in-house simulation tool SLOW, we are able to run efficient real-time simulations. And with that model, we build a Kalman filter, which is a method to do sensor fusion and indirect measurements. And with this physics-based approach, we get a white box, which gives us more transparency and quicker adaptations. However, we still see the use case of AI in post-processing, for example, to detect anomalies or to forecast the remaining fatigue life of the mooring lines.